I'm here at Lang.Next, which is a wonderful conference that Microsoft puts on for free. Thank you very much, Microsoft. And invites wonderful people for great talks and a great community. And I'm Carl Hewitt, and I'm emeritus at MIT, and I currently visit at Stanford. And I work with companies in the Valley trying to get this technology out into the world. It's quite challenging. And we're in the midst of a huge revolution. For starting off being a hardware revolution, namely the thing called the many cores. You come the revolution, right? You first hear mutterings, right, from the detectives, right? And then you start to see a few people marching in the street, okay? And then they storm the barricades. Well, we're about to storm the barricades, and it's the many core revolution. It's the fact that we now have a completely different architecture than we had 20 years ago. We now have many computers on one chip, okay? Currently they're shipping 16, but it won't be long before they're shipping 100 extremely powerful processors, process anything in the world, on one chip. They're called many cores. And that is, of course, going to cause a huge revolution in software. And so, I'm trying to help make it happen. Thank you.
I'm Dave Ungar. I'm here for the conference. I'm having a great time. Thank you, Microsoft, again.
Thank you.
I have been in IBM research now since 2007, where I'm having a ball, and spoke about some work that we did last year with Harold Osher and Doug Kimmelman on subjective objects. I worked a lot on efficient implementations of Smalltalk and Self, and that work is now used for Java and JavaScript quite a bit, along with my students and employees and colleagues. Randy Smith, who was a co-designer of the Self language, changed the way I think about systems, because he builds things that people can easily use in unanticipated, interesting ways. And the Self implementation work, I'm really interested in systems as Disneyland rides, not language systems. Giving you a coherent experience, putting you in an artificial reality in every aspect, and that has lots of interesting implications. So I did some work on cartoon animation many years ago that was significant. But the self-implementation work was made possible by C++, which was the implementation language we used when we wanted to have control over what the hardware was doing and get it to run fast, but we still wanted the object-oriented paradigm. And so in our project, we were somewhat early adopters in the late 80s of C++. And with that, let me pass it on.
Very nice segue. I'm Bjarne Stroustrup, and I'm at this conference too, and enjoying it. Meeting old friends, among other things. And I did C++ while I was at AT&T Bell Labs. Then I spent 10 years in academia, Texas A&M. I'm still associated with them, and I'm also a visiting professor at Columbia now. But I just returned back to industry, and my primary work is with Morgan Stanley, which is a huge computer IT operation in New York and other places, and they're back.
Right on.
I am right in the middle of changing careers, starting my third career, so I don't have any sort of grand visions just now. I'm also just helping to finish the next version of the C++ standard, C++ 14, and there's a lot going on there.
So one of the interesting things in your keynote, you mentioned the importance of systems programming languages like C++ and C and other ones, is that they bring you close to the machine in terms of taking advantage of what it has to offer. But the machine has now, according to Carl, and obviously he knows what he's talking about because it's true, is starting to evolve into this many-core thing. So how does C++ change to take advantage of machines with 100 computers inside?
Does it? First of all, one of my main points of this talk was that you can't have a single language that's best for everybody and everything. And I was focusing on C++ as something to deal with the hardware at the hardware level, and then providing abstractions on top of that, because bits and bytes are not very pleasant to deal with all the time. In terms of concurrency, C++11 gave us a type-safe version of the traditional threads and locks and lock-free programming kind of code, which is a necessary foundation for getting further, and probably the worst way of dealing with concurrency, but that's what we mostly do. And there's a lot of work for the next level of C++, which would be C++17, where we're working on various forms of higher level concurrency models, which we can now implement as libraries because we have the foundation in place. And so we expect to get sort of work stealing stuff. We expect to get some parallel computation. We're expecting to get transactional memory. We're going to get better ways of communicating and synchronizing things. I think Carl will appreciate that we put in futures in the previous version, C++11, and that really took a lot of arm twisting on my part to get them in. We didn't get them quite right, but it's sometimes much more important to get the right idea in, even if you get it done wrong. So we'll have it fixed for 17. And so the way we're going to deal with what you said is first to basically be able to model a single core and a single thread running on a core, and then communication between those, and then go further into specific models that may be application specific and maybe be general.
So I wanted to say something that I wish you had said, but I'll say it for you. You know it so well it needs known. You wouldn't think to say it. Parallel programming is performance programming. The reason, if you didn't need performance, you would just run serially. And one of the big strengths of C++ is it gives you that performance. You can get as close to the hardware as you need to. And so I think that's an important thing for me when I think of taking advantage of these machines and C++. And the other thing that was implicit in what you said is that C++ is a language that has a great strength that you can program in many different models with C++ in many different ways. And since I wouldn't say there's a consensus yet of how to handle these greatly parallel programs, I was looking at a way based on no synchronization emergence a couple of years ago. And whatever way you choose, you can most likely try it in C++ and get the basic performance so that you know there's no point in taking a slow interpreter and running it in parallel and saying you solved the problem.
Yeah,
I'd like to disagree a little bit with what Dave said. I don't think that the many cores is just a performance issue. Of course, if you truly didn't care about performance, you'd run a Turing machine. But it really is a game changer in the sense, if you think about it, I mean, we're going to have 1,000 threads per core and 100 cores. That's effectively 1,000,000 things going on at effectively the same time within a single chip. That is a game changer, and it means that we need whole new kinds of programming language to deal with it. You cannot deal with this with that level of complexity and that level of things going on at a low level. I mean, ultimately, of course, the high-level stuff has to map down to low-level stuff where you deal with the bits and the bytes and the threads and the locks, okay? But unless we have whole new levels of programming language where we speak in terms of goals and assertions and plans and talk to it that way, we don't have a chance. So that's our task now. I mean, the programming, each time, if you're going to have a long career, in computer science, which I've had, fortunately, it's just dramatically changed because I started off punching cards, right? Then I was dealing with these magnetic tapes. Then we had this single-user PDP-6. Then we had the PC. Then we had servers, right? Okay. And then we had object-oriented programming, right? Each time, Moore's Law is this amazing thing. It's exponential growth, okay? It's like the eggplant that swallowed Chicago, right? It gets bigger than Chicago very, very fast. And it's just a total game changer. And we're about to go through another revolution.
My view is that revolutions don't happen as often and as fast as people imagine, because there's a lot of inertia there. I agree we have to deal with these 100 and 1,000 core machines, but I don't think we know how to build a language to do that. And one way of getting there is to build an environment where you can do a wide variety of concurrency models and ways of handling them and experimenting with them as libraries. So my view often is, instead of building a language, first you build libraries in the plural and try them out and see how they coexist. This is sort of the C++ low-level alternative to the higher level model. And anyway, I see my role and the systems programming role as foundational. We're not going to build the application language of the future, but I would really like to build the implementation infrastructure that goes under it, whatever it is.
Yes. Awesome.
Let's talk about Kristen Neugar.
Yeah.
I was better explained. We were sitting over a beer or two last night and discussing various
What a collection of characters to see at the table.
That's right.
We all knew Kristen Neugar,
Yep.
who invented object-oriented programming. This is where we got words like class from.
That's right.
He was a mathematician background, right? So he wouldn't use the word type and things like that. Anyway, he was, of course, a professor and a computer scientist, but had a major contribution to politics also. He was always close to the labor movement. He was always working, trying to get fairness and distribution of information in reasonable ways, privacy issues. And he was also the individual that did most to keep Norway out of the European Union, which I thought was a good idea for him. And he was a great guy. The discussion we had here of technology and the policy issues that has to do with technology goes way back and to our common friend Kristen Neugar, who was one of the really pioneers in looking at the policy implications of technology.
And when did you meet him, and how did you meet him?
I met him when I was a grad student in Aarhus, and he used to come down from Oslo about once a month, and the apartment where guest professors stayed was the stairs were just outside my office. So basically he comes in and he yells basically to me, saying, "Round up the usual suspects." And so we go up and we sit around the table and we talk. That means Kristen talks, because Kristen was a very responsible, feeling duty kind of guy, and he was a senior professor in Oslo. And you have to be respectable and proper and all of these things that Kristen was not very good at, because he was a great guy. He was sort of larger than life.
Yes.
I mean, 6'4", probably, just as wide. Big guy.
Right. Yep.
And so I realized, after having gone through this a couple of times, that he has basically been under a pressure cooker up in Norway for a month. And he comes down, he sits down with a bunch of students, and it just gushes out of him. And that was how I learned object-oriented programming and quite a few other things as it was going on. I got it straight from the horse's mouth, as it were.
Wow.
And I remember seeing you give a talk at Bell Labs when I was working at Home Dell in the late 70s, and the impression I got was you were trying to bring object-oriented programming to Bell Laboratories. It was an early talk on C++. Was I mistaken, or?
No. The emphasis was not on object-oriented programming as such. I wanted to bring better control over code, more expressiveness over code, down to the level of the hardware, where we can do with a lot of help.
Mm-hmm.
And object-oriented programming, as learned from Christian Nyborg and applied in my PhD work and such, was my main tool for that. And interestingly enough, I was just reading somewhere that the languages that came after Simula seem not to have concurrency as one of the major principles, which was one of the good things that was in Simula. It was not just the classical object-oriented classes and hierarchies. It was also concurrency. And so, in this context, I'd like to point out that the first C++ library ever, so the Hewitt classes library, was a library for running little tasks in parallel. And I was running 700 individual tasks on a PDP-11. And I got up to 3,000 when I got a real modern machine with 1 megabyte of memory and 1 megahertz of computing. So concurrency was a major issue to Christian and also to my early work. And it basically paid for the development of C++ for the first 10 years. I was really good at writing programs, simulations, and similar things that requires a few hundred or a few thousand separate tasks. That was my bread and butter.
And is that how you got Bell Labs to fund the work?
Oh yes. They liked people who could help build things, and so we're doing things like trying to figure out what the buffering capacity for a network would be for a small town. Somebody wanted me to actually simulate Manhattan. It was a bit beyond my abilities at the time. And we were doing things like board layouts, which was also done with several in parallel. This was a pseudo-parallel in those days till we got hold of multiprocessors, and we could have 6 or 8 processors. But there's a lot of that in the history of programming languages. It wasn't invented yesterday.
Mm-hmm. So I first met Kristen, a little bit of background, after I designed this language called Planner, which had been then used by Terry Winograd in a fantastic demo at MIT called Sherdlu, right? Except the Planner it was message passing, right? But it wasn't efficient message passing because it was a kind of a broadcast model where you'd broadcast a goal, not really broadcast, but you'd put it out there, you'd publish a goal, you'd publish an assertion. And it wasn't fast enough. And then we invented actors as the concurrency primitive. And we wanted a programming language for the actors, right? And they said, well, you've got to learn Simula. So I went to the library and I found this book by Bert Wissel, and it was really hard to figure out. But fortunately, at this time, we began to, concurrency became a thing. There were lots of it. There were several of us interested. We had different approaches. We had one approach called actors. Robin Milner had his approach, and Tony Hoare has his approach. And we all came together with this marvelous set of seminars organized by Kristen, okay, in Aarhus. And so I'd sit up late at night, okay, drinking aquavit with Kristen, debating the issues. And I said, Kristen, you've got this nice simulation engine, but it's not concurrency. You've got a global clock that ticks it off, and you only run one simulated object at a time to do its thing, and then you advance the clock and let the next simulated object do it. And that's not concurrency. Okay, I want all these actors to run at the same time and send messages back and forth to each other. And that is not Simula. We need real concurrency. And so we debate the issues, right? Become a little bit more less coherent. And I never convinced him.
What did he say to that?
he said to that look, he was all about simulation, right? He says, first of all, our simulations have to be reproducible. So if we don't have a deterministic way to do this, right, says, how are you going to debug these actor systems if you don't have control over the situation, right? So that you can reproduce the bugs, right? I said, well, how do we run our society? You can't restart the whole society. How do we find bugs in our society? We observe, we keep record, we keep careful records, and we try to improve, right? We can't turn back the clock. That's just impossible. Welcome to a brave new world. But in return, we get an enormous increase in performance because you don't have to run one at a time. That's a huge bottleneck. But Kristen did have a colleague, Ole Johan Dahl, who invented this marvelous compiler technique that defeated the whole Japanese fifth generation. You might think that if you have this hierarchy of objects with this big tree, that when you get down deep in the tree, there's going to be a lot of bureaucracy, invoking an object down there. Ole Johan Dahl invented this thing called the V-table, so that you can invoke the thing in just a single procedure cycle. It's just one indirect jump, okay? And that enabled us to have, in this country, in object-oriented programming, these big trees run efficiently. Over in Japan, they took note of Prolog and said, we'll do it that way. So they had the world's slowest procedure call, and they were just completely defeated them. There was no way to get over that initial mistake. So Ole Johan Dahl defeated the whole nation of Japan.
Now two things have piled up in my brain. One is there are other techniques besides V-tables that, depending on the context, are easier or work better. But rather than delve into the details, the more interesting thing for me at the moment is thinking about the different ways of thinking about computation and parallelism. I mean, you came up with actors, and many, many, many systems I admire follow that approach. And let me characterize it in my own way, because I want to say something else, and then you can jump in and correct me. But the insight I took away from actors is things that are parallel are just too tough to think about, because any combination of things could happen, and that's a huge number as the number of things goes up exponentially. So we'll carve up the world into small pieces, each of which is serial, and we can think about them easily, and we will let them communicate. And we have to live with the fact that the messages that come into the pieces may come in different orders, and so things might not be reproducible. But get over it. That's reality. That's it. And there are other ways to deal with it. The Scandinavian school of thinking about computing, and you can correct me after I get it wrong, is it reminds me, my home is furnished in Danish modern because I feel that the furniture is designed for comfort and simplicity and elegance. And I've always thought of the Scandinavian school of software in the same way. I met Ola Masson, who was a student of Kristen, at a talk he gave about a language, Beta, which I really, really respect. It says, people have a way of thinking about the world, and we'll call it a model, that it's a nice, elegant, tractable way of thinking about it. And we will find a way to make the model run. That's our software, that's our program. And Kristen, because he was involved with the design of the first reactor, and you can tell the story better than I can, had to invent a way of programming where he felt confident he wouldn't blow up Europe. And so that's a whole nother, when you talk about the debate, it's just a whole nother take. And then there's the Alan Kay take, which is the one that kind of gets me right here. I love it, which is, let's give kids something so they can be really creative and build interesting, complicated things. And if it breaks, it's just a kid's experiment, so what? And build things that never were built before. And the small talk group invented things like overlapping windows because I think they had the right creative foundation. Okay, so now that I've probably distorted things, why don't you? I'll let you jump in first and correct my misstatements.
Well, I don't think you made any mistakes. It was, yes, the motivation for building Simula, starting with Simula 1, was Christen and Ole Johans experience with simulating the first reactor in Norway. And the point is that the fuel rods emits particles at a high rate, and you then have the dampers that absorb some of them, and the idea is to have an equilibrium. If too much is absorbed, the thing stops. If too little is absorbed, it can go boom. And so he really was interested in reliability. And in the sense of the emphasis on reliability and to some extent efficiency, I'm definitely in the European school of that. What I think about as an interesting application has more to do with controls of a car and an aeroplane or something like that than a kid playing. If a video game goes down, probably that's a good thing, given some of the video games. And I'd like to point out that the C++ library that did concurrency, tasks, was they communicated not by calling coroutines. That was an underlying mechanism. They really communicated sending messages through message queues. And so that was the model I was using throughout. Unfortunately, it's really hard to get people to change their model of the way they think about systems. The task library in C++ was very successful, but various people that picked up C++ didn't quite get it. And in particular, Sun did not want to ship that library because they couldn't see the use for it, even though it had been the bread and butter for the whole thing. There was some other example from what you were saying that made me think about this. Mm-hmm. But changing people's view, it was Beta. Beta is a beautiful language which the students by and large hated and didn't understand, and nobody basically outside Christen and Ole Lehrmann's group really got it. I think I have convinced somebody that it was good because they stole my copy of the book. But the point is that was different it was sufficiently different so that, for instance, most people in the object-oriented world rejected it because it wasn't like what they were used to, even though it was done by Christen. And by the way, I was an undergrad together with Ole Lehrmann the same year in Aarhus, so it's a small world.
And I can say a word about teasing Ole Lehrmann and Christen about concepts and phenomena. If you can wait a moment to correct my misstatements about actors. One facet of the way they thought about modeling the world, as I understand it, was that there were concepts like the value 3. It's everlasting, it's perfect, and then there were phenomena like this table, it's a thing, the interview is happening, and coming from the self world, I would always tease them about it. I would say, but because a phenomenon which corresponded to an object and a concept, kind of a class or a pattern as they called it, because you can get a concept from a phenomenon and you can get a phenomenon from a concept, but you can't go down, you can't get a phenomenon from a phenomenon. I said that's an asymmetry. You can get the concept of a concept, you can't get the phenomenon of a phenomenon. And so I would say, get rid of the whole thing, unify it, just have prototypes and copy them, which was my youthful way of teasing. Not that the other isn't useful; it certainly is. But I just loved to tease actually both of them, and still do. And Ola teases me right back, of course. So thanks for letting me get that in.
Of course.
Yeah. Yeah. The key thing about the actors is their decentralization. Because basically in 1973, I used to know this guy called Vince Cerf, who was one of the inventors of the protocols for the internet. And one of their tasks from the DoD was it had to be decentralized, right? They weren't worried about nodes going down. They weren't worried about computers going down, disrupting the communication. They were worried about them being blown up. So they designed this decentralized thing, and the actors are the software version of that. Each actor independently processes the messages that it received. So you can think about this in organizational terms. And it's very important to understand the difference between parallelism and concurrency. Parallelism is a top-down thing. You have this thing, it propagates down, and then you gather all the results back up, and then you do it again, right? Whereas concurrency is like a human organization in which the branches of the organization, the units, are allowed to talk to each other. They don't all have to go through the CEO. Marketing is allowed to talk to sales, is talk to engineering. The various people on a team of engineers are allowed to talk to each other. All communication doesn't have to go through their boss. Now, it's exponentially faster to allow the pieces of an organization to talk to each other as opposed to requiring all communications to go through the boss. And that is the power in terms of performance, and the power in terms of organization is that now you can semi-independently design the various pieces, okay, to directly communicate with each other. And so now you decentralize the design as well as the actual physical communication. And that's the power of it, is that it's power in performance and power in architecture.
Intriguing. It seems like a great model for where we find ourselves today with, have to use the term because everyone else does, with cloud computing. Why aren't actors more prevalent in, when you think about the type of concurrency and parallelism and distribution that's required in, say, Google and Microsoft and everywhere? Why aren't actors...
Latency. If you're going to be entirely message pass driven, okay, it has to be that the latency between sending a message and receiving and processing a message has to be extraordinarily tiny. And so if you have two computers with a wire in between, the latency is enormous. You can do things faster in terms of loads and stores on one machine than you can ever ship a message to the other machine and get a reply back. So it was only when we had the many cores with the coherent connection between the cores, okay, so that you have nanosecond latencies in sending messages, that it finally becomes fully practical.
So that's why you're so into the whole many core.
That's right. Finally, after, what is it, invented in 73, right? 40 years later, we're getting ready to go.
Why message passing systems are not more popular is a very good question. I haven't spent 40 years with it, only 30. And people seem to want to use shared memory even when they could do message passing efficiently. And the best, if you have to go through a wire, there's a fixed cost, and if you have to go through it, you have to pay it. That's not a problem. But if you actually have a memory that's shared, you have the choice of communicating with shared memory monitors, synchronized data and such, or messages. And the performance difference is not that high once it's in the same memory. And I'm not sure why people traditionally have been so keen on using shared memory as shared memory, as opposed to organizing their systems a little bit more nicely and communicating by sending messages and getting results. and you can put all kinds of nice sugar on that to make it look less like
Excuse me.
putting a letter in the mail and sending it. It can look like futures. It
Well,
can look
yeah.
like
Now,
cues.
It's
There's many ways.
Partly it's a matter of the programming languages were developed as load store architectures. The so-called von Neumann, it's all load store, right, as opposed to message passing being primitive, right? And so there's the drag of that legacy, right? And now a shared variable that you do assignments to is becoming a very expensive. But previously it was the cheapest thing. Now it's the most expensive thing because that memory location has to migrate among all the cores if they're all going to do doing stores on it. That's enormously expensive. That's one point. The other point is that if you look at the way that this coherent memory among the 100 cores is actually implemented, it's actually implemented as a message passing system in which they send cache lines between the cores, right? So that's why there's no longer such a big difference in performance between real message passing and storing, because it's all built on the same message passing substructure.
So I have a slightly different view. Because I looked at harnessing many core stuff briefly about a year or two ago. And my feeling was, if we do get huge numbers of cores on a single processor, or maybe we already have it, synchronization is a bottleneck that has to be eliminated. And what that means is dealing with memory systems that are not so coherent and not doing message passing, because message queues require synchronization. So I did an experiment where I modeled a multidimensional spreadsheet in which the intermediate nodes wanted to cache the computed results. So if you asked for a result that was computed based on some other result that was computed, if it was the first time you asked, all those nodes would cache their results for the next time. But if you changed some of the raw data, they'd have to invalidate, and the normal architecture would synchronize that invalidation with the request. Otherwise, you could miss an invalidation. And even though the leaf changed, the cache of computed data would be stale forever. And so the standard way of doing this is to do some synchronization. And being me, I said, forget about it. We won't synchronize. We'll let these things hold stale data, and we'll just take some of the extra cores and we'll let them run around and randomly recompute all the cached values. And so I can probabilistically tell you how stale something might get. And that was an example of replacing synchronization. I know other folks have been doing this for years. They call it eventual consistency, maybe, or that's a related concept. So I think that in many core systems, the overhead of message queues for the canonical actor model may be prohibitive unless you let them be unreliable. And if you let them be unreliable, I think you get rid of that synchronization overhead. Now you disagree, which is great. It'll make for a good video on the net.
Exactly. Because we know, it turns out that implementing these actor systems is an enormous, to do it efficiently, is quite an enormous engineering enterprise, okay? Because you have to really have very effective runtime systems, and you have to have new programming languages. Now, the runtime systems, this is work done in the last year. We now know how to implement actor message passing perfectly reliably, okay, lock-free. It means that you never hold a lock.
It's not good enough.
It's pretty good. Holding locks is a terrible idea, you'll admit that.
Well, unless you're holding a bagel and cream cheese.
Lock-free.
So there are lock-free implementations now of the actor message passing between them, right? And then the way that since the actors process the messages, so you do not want to expose the following in your programming language. Don't expose threads, terrible idea. don't expose locks. Absolutely terrible idea. Create a programming language in which you never can have data races among the variables. In other words, a variable in your program should not be able to change out from under you. That should be impossible. And we now know how to do that. So it's been a long road, but now I think the engineering is up to the task. And I do think that lock-free implementations of message passing is an important advance, and it makes reliable message passing possible.
It's old hat. We've been doing it for at least the last 10 years. I mean, it's on Mars already in the probes, and they don't really like experimental software.
No.
It's all over the place.
So
lock-free data structures
amongst your 100 cores, okay, you can send message passing extremely efficient. You can do message passing extremely efficiently, lock-free.
Yes.
And I've looked. There was no algorithm published before this year when we published ours that did that. We looked at the literature. There is none.
So I published a lock-free vector that grew. About
To do
8 years
general
ago.
message passing.
So
amongst actors.
let's be clear what lock-free means.
Yeah.
And I may get it wrong, and you guys can jump on me if I do. But my understanding of lock-free does not mean synchronization-free.
No.
There is still synchronization involved. Synchronization involves communication between cores, or communication between cores and some more centralized thing on the chip. And what I'm looking at is as things scale up, and we want to do these things often, if we don't pass a message that often, we can afford that. But what do we do when we don't want to do that synchronization? And that's where I say non-coherent memory systems and unreliable message queues seem to me, I don't see any way out if we're not going to pay that low-level cost. And so I'm not saying that the lock-free implementation you're talking about isn't a great advance, isn't much more efficient, may be plenty fine today at a certain scale with a certain amount of computation in between messages.
I think it's probably important to explain what a lock is. A lock is a word of memory, okay, in which you can set the lock, right, and release the lock. And in between the time when you set the lock and release the lock, you hold the lock, okay? And in general, you have to have, this lock can be contended. So there can be lots of cores trying to set the lock at the same time, right, identically the same time, and only one of them wins, okay? The others then have to wait for the lock to be released, okay, and then one of them gets in, right? That is called programming with locks, okay, and that is inefficient. Now you can do message passing among the actors so that they can all be sending messages to the same actor, right? And you never hold a lock. That's the invention.
But you do spin.
You never spin. You do not spin.
You do synchronize.
You do not spin.
You do
Spinning is
synchronize.
bad. Don't spin. Spinning means that you have this somebody else has got the lock, right? And all you can do is you can try to get the lock, right? And then try to get the lock, and then try to get the lock, and that's called spinning. Do not spin. Terrible idea.
But again,
It actually works very nicely sometimes.
Yeah.
Depends on what your problem is.
Depends on what the contention is.
It's just also, you're talking about how to avoid synchronization.
Yes.
It's a matter of granularity. There is essentially nothing that runs faster than a straight piece of code running on one processor, flat out, with a nice hot cache. And so if you have chunks of work that are big enough, you get rid of the synchronization simply by not having that much concurrency. I'm saying that as somebody who wrote really efficient system with hundreds of independent tasks on things that today wouldn't run a wristwatch.
They were coroutines, right?
What?
Only one of them ran at a time.
Yeah, except when we got more processors. But the point is that there are many ways of looking at this. The incoherent memory is good, and it's used in some cases. But we shouldn't forget that a simple, old-fashioned program that just runs flat out is probably the most efficient way of using just about any machine architecture we know of.
Well, just to tease you a little bit,
Yeah.
there's something more efficient than that. And that is a simple program that runs flat out unreliably.
Yes, if it doesn't have to be correct, I can make it as fast as you like.
Yes.
No.
And so
We have to sign up for indeterminacy, not unreliably. Indeterminacy means, for example, we have a whole bunch of people working together, right? And the order in which the actions, the message is going to be processed is totally indeterminate, right? It's up to quantum physics. I mean, okay. But it's not unreliable. The people coordinate with each other, and they reliably get things done. For example, the four of us had to coordinate to come here, right? There was never any doubt in my mind that we would have actually reliably succeed in doing this coordination and actually film this thing, right? So the unreliability was out. Now, the exact order in which we got together, right, and exactly which room where we were going to, that was indeterminate. That was not determined ahead of time. And if somebody else had been in this room when we arrived, we would have gone to another room.
But the camera was in this room before we got in.
We would have taken the camera with us. So it was indeterminate what was going to happen, but it was very reliable.
Looking at the world today and reading the newspapers, I think we screw up very reliably and very often.
Yes.
The systems we have developed are not actually some that I would like to see replicated in my computers. I would like my computers to be more reliable, more predictable.
But I would say that the way to make them more reliable, just thinking of my experiment, is to put the reliability back in at a higher level. So, even the lock-free algorithms involve synchronization and communication between cores. They use atomic instructions. They're locking down at a very low level.
It's just an efficient form of logging, but it's still logging.
So
you can avoid deadlocks. That's a good thing about them.
Yes. So what I was interested in is, we'll let the low level be unreliable, and we'll have this higher level mechanism. In this particular case, it was trivial. I just had other cores go around correcting mistakes. I mean, you look at DNA replication, it's sort of fundamentally unreliable. They're repair mechanisms. And the whole thing, I mean, we get software errors and various diseases and die, but on the whole, it's pretty reliable. So it's an interesting, it's what I call the where to sweep the dirt under the rug problem. Where you put the complexity in the system, where you put the unreliability, and it's a lot of what engineering is about.
Yeah. Building reliable systems out of unreliable parts.
Yes.
That was one thing I learned at Bell Labs. That's what we do.
Yes. Mm-hmm. Well, I think that determinacy is out. It's going to be indeterminate. Determinacy is definitely out. Reliability is basically unachievable in its pure form of getting it right. What instead, we're going to have robustness. Okay? Robustness means recovery. Mm-hmm. It means articulation. It means making adjustments. It means negotiation. Okay? It means all of these things, right, as a way to achieve robustness. It's not as pretty as top-down control reliability, where you think you're in control. You're definitely not in control. But it's where we're going, it's what we have, and we have to learn how to do it better.
And to that end, I would commend, if you're watching this and you haven't read Martin Renard's papers, he has written many wonderful papers on robustness. R-I-N-A-R-D-S is how he spells his last name. One of the results I love is he took several applications and mechanically changed all the for loops in the application. If it said less than, he made it less than or equal. If it said less than or equal, he made it less than. So the loops were running either one more or one too few times. And he probabilistically just change some set of for loops. And the interesting question was, how high a percentage of loops could he change and the program still work? And the amazing result was, and I don't remember the exact number, something like 90%. He could change 90% of the loops. And now these weren't putting data in persistent databases. These were an email reader, a video, playing back video files. But what I took away from that is we don't have correct programs today. We don't have reliability. Everything is wrong. It's just acceptably right for its use. And he's gone on to do a lot more work in this area. I commend it to your attention.
What's the most interesting problem that you're working on, or that you think needs to be worked on, or something that you've been thinking about?
One of the reasons I got back into industry was to get closer to real-world problems, because academics have a tendency of drifting into some space where they refine and abstract the problems, and in the end it could be something totally different. So I will be much better at this question in about 2 years, when I feel I'm back in at the coalface and has more experience. But my overall aim with C++ in the next few years is to make simple things simple. You can't make everything simple. Some things are really complicated, some things are really important. You can't simplify everything. So I want to make simple things simple without making the complicated solutions impossible. And one of the areas where most of this will happen is exactly concurrency. We need the model for how to program things, and beyond that, then we need a way of organizing our systems. A lot of what we are doing scales to 10, 20, or 30 cores, and it's basically independent tasks being executed, communicating, as Carl said, without explicit threading and without explicit locks. There will be some synchronization under the hood, but we would rather not have to say what it is. And I'm going to put a fair amount of work into that, and I know the Standards Committee will be putting a lot of work into that. And the reason I know that is, of course, I've seen the initial proposals, and I know that a lot of work's going on.
Excellent. Thank you.
What's the most interesting problem? Well, the first problem is why. Why are we writing programs? Why are we building computers? What is the value system? And that will be different for different people. But I think that's a very interesting question. What I find motivates me are things that help me be creative. So things that feel like they're less effort to use. And the state of the art in languages and interfaces seems to be, for the most part, and Smalltalk was an exception, and I think Self was an exception, we're hindered from being creative. Every time you go to your computer and you have to type in a password, and you have to get it exactly right, letter for letter, that's stealing some of your cognitive ability that you could be using to be creative and solve your problem. Every time you have to wait for the computer, and if it's just happening on the computer, there's no excuse for it, in my opinion, especially now with solid-state disks. That wait is stealing some of your ability to create and solve that problem. Every time in a programming language you have to think about stuff that you don't have to think about for one reason or another, it's stealing some of your ability to think about what you'd like to do. We even had a talk today by a gentleman, I think Mark Miller was his name, every time you have to hit the shift key to type a punctuation character in your program, that's stealing some of your ability on the motor coordinate level. And gosh, I like to say that all of us computer users and programmers have battered wife syndrome. We're abused all the time by the interfaces and the languages, but we're just so used to it, it's become normal. And
Can I get a chance to disagree with you?
well, yeah. So let me just
Yeah,
wrap
when you
up and
finish,
say,
yeah.
I would
I like this.
love to change this. I have tried in the past. I have not succeeded very much at all. But that is the thing that really motivates me, because creative people do such amazing things. I love it. Okay, now.
For oppression, I'd like to pick up on what you just said. Namely, the thing that I'm most interested in is the future of freedom as a concept that we've had so far, and maybe a brief, illusory, temporary phase of existence. And that's what's on the table now. Because right now, we live at the mercy of internet intruders. We've created this thing. Computer science has failed us, in my opinion. Just completely failed us for us to be in this position. We're at the mercy of hackers. We're the mercy of states, okay, that are spying on everything we do. Universal surveillance, okay. And the big companies are vacuuming it up and selling it. I mean, the FTC has just come down and said, here are the amazing things, all the information is for sale about you, right? So the question is, it seems to be it's our duty, our solemn duty, okay, as a science to make up for this terrible tragedy. That if you want to look into the abyss, there's a very nice book by Anna Funder called Stasi-Land, which says exactly what it was like to live under the Stasi, okay? And that was just the hack of it. They interviewed this Stasi guy, right? And he said, hey, look, if I had the technology that was available today in the GDR, right? Boy, could we have done a good job. We wouldn't have had to hire, we wouldn't have had to abscond with 20% of the population to spy on everybody. We could do it using technology, right? We could make 1984 look like child's play. And that is what we are up against today. And it has to be a technological solution. Because if there is, power will be abused. If they have the power to do it, they will do it. Like, for example, they asked the Republican in the House, why did you impeach Bill Clinton? His answer was, because we could. And the answer is, if they can, they will. So it has to be a technological solution to preserve our freedom. Nothing else will do.
Okay. I wanted to hear your disagreement.
Yeah.
Yeah, it, I think, was more a different point of view than a disagreement. I don't think I chose the word right. First, I agree with you about the keywords. We have done a denial of service attack on ourselves with all this security. It may be necessary, but it doesn't work either. So it's really embarrassing. No, I'll just get to, you said about motivation. Mm-hmm. And my motivation is so different that I thought it would be worth mentioning.
Great.
I'm not actually very interested in improving the creativity of people. People will find outlets for their creativity. Mm-hmm. And I listened to that talk about how to save keystroke. And you know, I'm a very best typist, but I can still type faster than I can think. Mm-hmm. And so that is not where the bottleneck is. It may be in the reading, but it's not in the writing. Mm-hmm. And finally, when you talked about motivation, through my head went what actually motivates me.
Yeah.
And which is really nice applications. It's not actually the language itself. I'm a tool builder, and I take most of my pride and pleasure out of the things that are built using my tools. Well, I'll take credit for self while I'm at it here. In that way, I enabled something that's important. that I enabled some of the stuff that goes on in the Mars rovers, the scene analysis and autonomous driving subsystems on C++. I'm so immensely happy that this happened. There was some C++ in the Human Genome Project. Great! Cars are now getting more reliable and safer because of software running on the cars. The gadgets are such a wonderful idea. So that inspires me, that keeps me going. And when I see what they're doing with the internet, I get a bit depressed because that's the converse of what I would have liked to see. I mean, if the service is free, you're the product.
Yeah.
And so I don't like to be in that kind of stuff.
So
but the great applications, the tiny little help that I have been able to do to science. The day they found the Higgs boson, I got an email message out of CERN simply saying, thank you. I mean, you could have a whole career out of just that.
Yeah. Right.
I mean, I've done something and it was important and it was good. I helped those guys find one of the fundamental things in the structure of the universe. Just a tiny, tiny little thing.
So is it the science? I'm curious. What's the difference between a great application like finding the Higgs boson and something that doesn't appeal to you so much, like the current state of the internet? Can you put into words what is the quality of the applications that really give you that pleasure and that feeling?
I think it has a lot to do with feeling it makes life better for somebody. That's part of it. But science itself is just, it doesn't necessarily, I don't think finding Higgs boson makes life better in any reasonable way. It's an intellectual thing. It's just wonderful. It's like going into some math and finally understanding a theorem, and when the light bulb goes on, that's important. So there's a science thing and there's the sort of utility to humanity. And a lot of the web apps I don't think actually help people. They waste time, distract people. They belong in some kind of semi-perverted entertainment industry. And so those I don't take pleasure from.
But in terms of C++, and everyone knows this, and it was talked about at this event by, the people who work at these places, but we could argue that Google has been relatively important in, say, the world of search. And Facebook's been relatively important in terms of the world of freely giving away your privacy. In a good way. Sometimes it's nice to share with people you care about, and you are giving away your privacy. And they've done a really wonderful thing, and they have wonderful engineers. A lot of all of that infrastructure is C++.
I know.
Windows, Mac OS, not Linux, whatever his name is, the Linux guy.
There's still some there.
You understand what I'm saying? It's everywhere. It's ubiquitous.
Yep.
Now, for me, it's not point solutions. Finding the Higgs boson is good, okay? Having a search thing is good, okay? But to me, those are just point solutions. The real action is improving the environment, improving the infrastructure, improving the community. Sharing is nice. It should not be necessary for us to give away our privacy. We ought to be able to share our privacy on a distributed basis with each other in communities like we used to. The information technology will support that. We have to get an economic model that works for that, right? But that's, for me, is where the action is. It's not in the point solutions. It's not in the individual superheroes, right? It's in the community, it's in the environment, it's in the infrastructure.
Cool.
I was not trying to make a statement about how to run the universe. I was trying to specifically reflect what you said about what motivated you, which actually I thought was a really nice thing, and the contrast was interesting. And by the way, the efficiency of C++ means that we have much fewer server farms. That's one of my contributions to the fight against global warming. Also the fact that a lot of the wind turbines are programmed in C++. Yeah, I'm very happy about that. That is where the social good comes in.
Excellent. Well, hey, you've all done wonderful things. which is why we wanted to get you all together in this context, which isn't as comfortable as a bar with a nice cold beer in front of you. But thank you so much.
Of linear aquavit.
Excellent.
That's right.
Yeah.
Thank you for spending time and for all that you've done for computing.
Thank you.
And it'll be interesting to see how this all pans out in the next 10 years.
It will
Yeah.
indeed.
Thank you very much.
Thank you very much.